In this video, we'll introduce the linear correlation between two variables. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. There is a linear correlation between two variables when we do have a correlation and the plotted points can be approximated by a straight line. So in our examples below, we see that there appears to be a linear correlation in the top two examples. In the first, there's a negative linear correlation, and in the second, there's a positive linear correlation. So in other words, in the first, as x increases, y decreases. In the second, as x increases, y increases as well. Below, here we see that there is a weaker positive correlation. It generally tends to be the case that as x increases, y increases as well, but it's less of an obvious linear relationship. Whereas in this last example, there is not a linear correlation between these variables. It does not appear specifically that as x goes up, y goes up in a way that is related linearly. We see that there are these values r given with each of these graphs, and the linear coefficient r measures the strength of the linear correlation between paired x and y values in a sample. It's also called the Pearson product moment correlation coefficient, or Pearson's R. Pearson, of course, discovered or invented it. And so here, so the value of R is going to be negative when there's a negative correlation. Here we have R is negative 0.1. It's going to be positive when we have a positive linear correlation. It's going it's going to be closer to -1 or +1 if those correlations are strong. It's going to be closer to 0 or just a smaller value when we have a weak correlation. And it's going to be very close to 0 if there is no linear correlation. Here is the formula for R. There are different versions of this formula, but here's just sort of the simplest way of writing it and in some ways thinking about it. R is equal to the sum of, in the paired data values x and y, the sum of the z-score for x times the z-score for y, adding each of those paired products together, and then dividing by n-1, where n is the sample size. I guess I don't have that written down. N is sample size. So let's think about why that works. So basically, we want to show that x and y either increase together for a positive correlation, or that as x increases, y decreases for a negative correlation. So what are the z-scores? Recall that a z-score is the number of standard deviations that the data value is above or below the mean. So these two data sets might be like on totally different scales, but we're just looking at what we're really interested in is how far above or below the mean is each data value. And the z-score, so if we have a positive times a positive, then that's greater than 0. If we have a negative times a negative, that's also greater than 0. So if we have all the positive z-scores together, all the negative z-scores together, then this will be a positive sum, versus if it's negatively correlated, we would have negatives with positives and positives with negatives. These would all be less than 0. It would end up with a negative sum. And so if x increases as y increases, then this is going to be a larger positive value. If they are all mixed up and there is not this linear relationship, then there's going to be a value close to 0 because the negatives and positives will cancel each other out. And if we've got negatives times positives and positives times negatives, if y decreases as x increases, then we would have a negative value for R. Some important properties of R is that R is always between -1 and 1. As we said, a value close to 1 shows a positive correlation, and a value close to -1 shows a negative correlation. A value close to 0 shows there is no linear correlation, but the variables could still be correlated in some nonlinear manner. After we calculate R, we must also check to see if this value is actually significant. So we can do this using hypothesis testing. We can either do this with a two-tailed test. So if we're just testing the claim that there is a linear correlation, that's a two-tailed test. And our null hypothesis, remember the null hypothesis is always like nothing interesting is happening here, this is boring. In this case, the null hypothesis would be there is no linear correlation, and the alternative hypothesis would be there is some linear correlation. We would use there is no correlation means that rho equals 0, where rho, it's the Greek letter rho, it's like a capital R, is the linear or the correlation coefficient for the population. So it's the true correlation coefficient that we are trying to estimate as compared to R, the sample correlation coefficient. So again, the alternative hypothesis would be that rho, the true correlation coefficient, is not equal to 0, that it's either closer, greater than 1, meaning a positive correlation, or less than 1, meaning a negative correlation. Or if we're specifically testing a correlation in one direction, if we're specifically testing is there a positive correlation or a negative linear correlation, then this would be a one-tailed test. And our null hypothesis would be there is no linear correlation, again, that rho, the true population correlation coefficient, is 0. Or and then we would have an alternative hypothesis, and that alternative hypothesis is either that there is a positive linear correlation, in which case the population correlation coefficient would be greater than 0, or there is a negative linear correlation, in which case the population correlation coefficient would be less than 0. To test these hypotheses, we're going to use either technology or Pearson's R table. This is based on both the sample size and the significance level of the test. So the table uses degrees of freedom, so that's really just the sample size minus 1. And as the sample size increases, the threshold for R decreases. So for example, if our sample size was n equals 10 was our sample size, we would use degrees of freedom is 9. If we were doing a two-tailed test, just testing for any correlation one way or the other, then we would be using a two-tailed test and say that our alpha level of significance was 0.05, sort of a common cutoff point. Then it would need to be the case that R was at least 0.602 in order to argue that there was some linear correlation between these two variables. So in this case, we would need R to be greater than 0.602 or R less than negative 0.602. So in either direction, positive or negative, this is just the absolute value of R to show a linear correlation in this case if our sample size was 10 versus if our sample size was more like 90 something. If n was 93, then we would just go with the smallest value that's close to this degrees of freedom. In this case, degrees of freedom would be 93 minus 1, it would be 92. So we would just use 90. And if we were still using an alpha level of significance of 0.05, then we don't have as high of a threshold for R. We just need R to be greater than 0.205 or R to be less than negative 0.205 in order to show that the null hypothesis is false, in order to reject the null hypothesis that there is no linear correlation, and to say, yes, it appears that there is some linear correlation between these two variables.